Hi guys, there's another question from section 1.8. This is problem number 27. So once again, we're given a function. This time is given in terms of y instead of f of x, which of course you know y is the same thing as f of x. Our function happened to be 3x plus 1 over 2x minus 3. Okay, so they want, in this case, now because we are using the variable y, they ask for what's called y double prime. Just like if you call it f of x, we call that f double prime. So now we're looking for y double prime, which is just the second derivative of y with respect to x. Okay, so again, as you can see here, we do have a quotient. So to get to second derivative, first we're going to have to basically start with the first derivative. So we're going to find y prime. So here they really have no option except using the quotient rule, which you learned from last couple of sections. So which says the bottom function. By the way, make sure you get the order correct when you use the quotient rule, because there is a subtraction involved. So you always go the bottom times the derivative of the top, not the other way around, not the top times derivative of the bottom. So it's always the bottom function times the derivative of top. I'm going to put the derivative again inside the bracket. Of course, derivative of 3x plus 1 is just simply 3. And then minus the top function, which is 3x plus 1, times the derivative of the bottom function. And of course, the derivative of 2x minus 3 is basically 2. And then all over the bottom is squared. Don't forget to square the bottom. So as you remember, this is what's called the quotient rule, which I believe is in section 1.5 that we already studied. So now we're just going to, so now if they wanted first derivative, of course, obviously you'll be done. Now you still want to kind of do some algebra here. They do want the second derivative, so I do suggest you definitely want to do some algebra to kind of clear things up. So I'm going to distribute the 3. 3 times 2x becomes 6x. 3 times negative 3 becomes minus 9. 2 times 3x becomes 6x. With that negative, of course, that makes it a minus 6x. And 2 times 1 becomes 2. With that minus again makes that a minus 2. But again, all over the bottom is square. So as you can see, in this case, the 6x and negative 6x kill each other. Negative 9 minus 2, of course, becomes negative 11. All over 2x minus 3 is squared. Now let me just pause here for a minute, because this is your first derivative. So of course we start with the quotient rule, and then inside we did some other basic rules, and of course simplify, clean it up, and this is what we have. Okay, so we're going to differentiate that once again, and that becomes the second derivative. Let me make a suggestion. Obviously, if you can see, you still have a quotient, a fraction, which means you can also apply quotient rule. I would not suggest that, because you can actually rewrite this a little bit differently, and then you can avoid quotient rule. You can just go to, I think, the shorter rule, the extended power rule. Okay, so let me show you that. Again, you do have an option of using quotient rule here, but I would not definitely suggest that. Let me show you how I would solve that, or differentiate that. So I'm going to rewrite that as, so here's what I'm going to do. I'm going to move the 2x minus 3 upstairs, right? Which means I'm going to change the sign of 2 to negative, and then, of course, you still have negative 11 in front. So you can actually rewrite the same exact expression by a little bit of algebra as basically negative 11 times 2x minus 3 to get power negative 2. So what you've done, basically, you have saved yourself some headache, because now you don't have to go apply the quotient rule, because it's a little bit more involved. You can just going to apply, well, this is just constant. So to differentiate this, it's going to be a extended power rule, right? So it's just a little bit quicker. So let me go ahead and differentiate that. So this is our first derivative. So now we're going to find the second derivative by differentiating this. Again, we're going to use the constant multiple rule. So that constant, as you know, it stays in front, doesn't change. And then multiply by the derivative of the function. The function is a function to a power. So once again, we use the extended power rule that says the power times the function, and then to the power minus 1. Minus 2 minus 1, of course, becomes minus 3. And then don't forget times the derivative of the function that is being raised to a power. Of course, the derivative of 2x minus 3 becomes 2. So there's your second derivative. I'm just going to clean it up a little bit. 2 times 2 is 4. 4 times 11 is 44. Negative times negative is positive. And then also, you still have 2x minus 3. Now, if you don't want negative exponent, you can also, I'm not sure how the back of the book leaves the answer, but I'm sure by now all of you know, you can also write the same expression as 44 divided by 2x minus 3 raised to the positive 3, okay? So anytime you have a negative exponent, if you want to make it positive, you just take it downstairs, and that becomes positive. So let me adjust this so you can see it better. 2x minus 3 raised to the positive 3. So now we're going to find the second derivative by differentiating this. Again, we're going to use the constant multiple rule. So that constant, as you know, it stays in front, doesn't change. And then multiply by the derivative of the function. The function is a function to a power. So once again, we use the extended power rule. So you can actually rewrite the same exact expression by a little bit of algebra as basically negative 11 times 2x minus 3 to get power negative 2. So what you've done, basically, you have saved yourself some headache, because now you don't have to go apply the quotient rule, because it's a little bit more involved. You can just going to apply the quotient rule. So basically, this is your final answer. Either one, of course, depends on whether they leave the answer with negative exponent or positive. So here's your second derivative, okay?